Hello students. So today in this class I am going to take one live example to understand the nature of gaseous state in particular and nature of matter in general. So let's say we have taken the example of cooking gas cylinder. Guys, you know that which gas is there inside the cooking gas cylinder? So that gas is the LPG, and that stands for liquefied petroleum gas, or sometimes propane gas. So LPG cylinders that we use in the for the purpose of cooking of food in our daily activity in the households, in the kitchen. So here you have to understand that liquefied gas, when comes out through a nozzle, it converts into the gaseous state, because we all have seen this in the gaseous state. However, inside the cylinder it is in the liquid state. So this thing you have to understand. This is again the example of interconvertibility. So here what happens, inside the gas cylinder, the gas is under a heavy pressure. High pressure is there. Because of that high pressure, this gas remains in the form of liquid. Now when it is released through a nozzle, it expands a lot, many times, and now it converts again into the gaseous state. So this is because of the pressure difference inside and outside, that liquid state gas converts into the gaseous state. Now this is one feature. In the another feature, you also have to understand that how it works. Let's say initially the pressure inside the cylinder is quite large because of the number of moles of gas inside the cylinder is more. You know that when cylinder comes from the agency, it is filled. Filled means what? That number of gas molecules are larger. And you must understand from the daily life example, from the balloon, that you have the idea of balloon, that when you put more air into it, the pressure becomes large. You also have the example, when you put more air into the cycle tube, the pressure becomes more. That means what? That pressure is directly proportional to the number of moles of gas. That pressure is directly proportional to the number of moles of gas, where N is what? Number of moles of gas. Now when this gas is filled inside the container, the number of moles initially is large, and therefore pressure is also large. Now when it is used up, obviously pressure becomes less, and when it becomes quite less, then we say that yes, cylinder is empty, and now again it goes for the filling. So in between all these events, we have to understand what science, what scientific application, what chemistry is going on, that gives a particular insight into the nature of matter. So here you must understand one thing, that the boiling point of this LPG is lower than the room temperature conditions. What I said that boiling point of LPG is less than standard temperature, that is 25 degrees Celsius. Now, if the boiling point is less, that means the gas will be in the equilibrium with the liquid state, because you know that at the boiling point what happens? At the boiling point, as I told you earlier, that at boiling all the liquids exist in the equilibrium with the gas. So, as that the pressure releases, as the number of moles inside becomes less, then what happens? This liquefied petroleum gas converts into gas more and more, and every time the pressure inside the gas remains almost constant because of this feature. Because of this feature, this remains constant throughout, and that is why we get a similar kind of pressure from the gas cylinder until and unless it becomes quite less. Liquefied gas and the gas are in the equilibrium because the boiling point of LPG is less than that of this temperature. So, what happens? That because of this we are capable to use almost whole of the gas which we have purchased. Now, if the boiling point is greater than that of this temperature, then some of the gas will remain inside the gas cylinder in the liquefied state, that won't come outside. So, this scientific fact we use for our value for money, we can say. Here, if this thing is reversed, then we cannot use whole of the gas that we have purchased in the gas cylinder, but because of this feature we can use this whole of the gas, and for that matter we have taken it. Now, as the gas is used, in between the cylinder is supposed to be empty, but in fact because of this feature the liquefied gas inside the cylinder converts in the gaseous state and it exerts the pressure on the boundaries. So, the pressure on the boundaries is the cause behind that how the gas comes through the nozzle. Just see, if the pressure is not inside the cylinder, the gas will not come, it will not ooze out from the nozzle. So, this property we have to use, we use in the cooking gas cylinders. Similarly, the same thing we use nowadays in the CNG gases also, that compressed natural gas that we use in the auto vehicles. And compressed natural gas is what? Do you know? CNG is what? CNG mainly contains CH4, compressed natural gas, and mainly it is methane. Same thing applies to the CH4 once again, that here this is this is the CH4 that is again stored in the liquefied state, and when it comes out it becomes gaseous. So, every time we are looking that because of the pressure difference, the interconvertibility is there. Similarly, we can have certain other examples where we use this particular thing. So, you know that one thing more that beyond that compressed natural gas, and one thing One thing more, that this is common, that both of them are the fuels. In case of fuels, what property should be in common? That they should be highly volatile, they should be combustible. So since you are looking that this is the hydrocarbon, this is also hydrocarbon, so both of them are combustible in nature. So combustibility is the common thing in both of these cases. And combustibility is the common feature for all the fuels. They can be in the gaseous state, they can be in the liquid state, because you know that this is the kerosene oil, this is the diesel, this is the petrol, all of them are combustible, but they are liquids, but these are gases. So in case of fuels, any matter, when it becomes a fuel, because all the fuels are also the matter, so any matter when it becomes fuel, when it has combustibility. Combustibility is when combustibility is achieved, when anything becomes combustible, so that you can understand on the basis of one particular fact, that all the combustible liquids must have lower boiling points. All the combustible, what I concluded, that all the liquid fuels must have lower boiling points. And yes, it is true. It is true for kerosene oil, it is true for petrol, it is true for diesel, and therefore you must have seen in the vehicles which carry these liquids, these fuels, it is written, it is mentioned that they are highly inflammable, and such substances are called as inflammables. They are highly inflammable. These are the substances which are labeled as highly inflammable. In case of gases, how to identify that this gas is combustible or non-combustible? So you must understand that all the hydrocarbons are combustible in nature. All the hydrocarbons. So you must understand this is a hydrocarbon, this is also hydrocarbon. So all the hydrocarbons, the another conclusion is what? That all the gaseous hydrocarbons are highly combustible. So here you can understand, you can cross check this thought, that whether it is LPG or it is CNG, both of them are the gaseous hydrocarbons, and therefore they are highly combustible, and obviously they will be again inflammable. So liquids, now let's say somebody asks that what should be the boiling, what should be the vapor pressure of any fuel, liquid fuel. So for any liquid fuel, if the boiling point is less, that means their boiling is easier. That means what? Their volatilities are higher. So this thing also you can connect that combustibility is further, you can connect this with the volatility. You can connect this thing with the volatility, that anything which is combustible definitely will be more volatile, and this also you can connect with their less boiling points, and this also you can connect the high vapor pressure. Now you can understand that these are the terminologies, and on the basis of that various questions can be formed, various questions can be fabricated, that yes, if the XYZ three substances are given, and for that let the vapor pressures are given, there may be a question that which one should be a better fuel. Let's say I am giving you one example. Let this is X, Y and Z. Let's say the vapor pressure of X is 300 mm of Hg. Let here vapor pressure is 200 mm of Hg. Let here it is 400 mm of Hg. Let somebody ask that which one should be the best fuel among these. So best fuel will be that which has the high vapor pressure, therefore Z will be the answer. So Z will be the best fuel, yes, this we have got, this will be the best fuel. However, if somebody wants to make the order of their combustibilities or order of their fuel characteristics, then what should the order? So Z will be better than that of X and X will be better than that of Y. You can understand on the basis of this example very well that how these terms you can connect together and how you can have a meaningful, a physically significant order of their fuel characteristics. So similar examples can be made. Now how to select a better fuel, also there can be question that which one is a better fuel, which one will have greater fuel efficiency. So the fuel which is better will always have better fuel efficiency, that out of less mass it is creating greater amount of energy, that we call fuel value. Let's say we have taken 1 gram of X, 1 gram of Y and 1 gram of Z. So if 1 gram of X is giving maximum energy, then what we will say that fuel value of X is greater. So fuel value is always the calorific value, the calories which are generated out of 1 gram. So matter which are of higher volatilities, which are of higher combustibilities, which are of less boiling points, which are of high vapor pressures become fuels, and the quality of fuel is measured in terms of their calorific values. Calorific value means what? Calorific value means the energy generated per gram of the fuel. Just write that this is the energy generated, heat generated per gram of the fuel. So this way, now we have gone through this topic in detail, that what is the matter, the definition, their particles, the constituent particles, their features, the distance between them, the force between them, and then their mobilities, then different kinetic energies, vibrational, rotational and translational, followed by the matter which becomes fuel. So these are the matters which become fuel, which have higher combustibility, which have higher volatility, which have less boiling points, which have high vapor pressures. So this way we can identify that which particular matter can work as a fuel. Then better fuels have high calorific value. What calorific value is? The heat generated per gram of fuel. So this is all about the fuels which become matter. So just have a thought upon it, and this is all about. So thanks.